one day want to have like some remedial math. So let's just start with some trigger warnings here. First of all, there's going to be some math in this talk. Oh, that's much better. Yeah, there's probably math in almost every slide. So, like, say it's called the remedial math, there will be math. And so hopefully some of it's going to be reviewed, some of it, hopefully some of it will be new for most of the folks here. It's going to be Python 3. I think when I first wrote this, it may have been a little bit more controversial. Hopefully everyone's on Python 3 now. It's like, I don't think there's anything with Python 3 specific to it. So you want to see something and say, well, actually, this is like quite the same, but I only have like an hour to get through everything, and so I'm going to be simplifying some stuff a little bit before we get into it. So this is an introduction. So I had a computer science, a PhD in computer science, but I worked in the industry for a long time, mostly at this company here. Like 20 years ago, I decided to go get my PhD in computer science, so I spent quite a while in academia. I spent like a year at a startup, then I came back to academia, so when I started in my PhD, I think I'd only been there like a week or two. I had a friend who said, this guy in my department is about to do his PhD defense. And you should come to it. Even if you don't know the topic, you should come to it, because you have to do this yourself. You need to see what the process is like. So this guy was in the electrical engineering department, and he worked on power system management. What that means is from about the second slide, it looked like this. What have I gotten myself into here? I think it honestly didn't look quite like that, but I'm pretty sure this was on about the third slide. This is, you know what this means, right? He's nodding his head. Something about real and reactive power measurements and Jacobians and bus voltages and angles and stuff like this. So
phasers.
Phasers, yes. Okay, phasers. So,
yes.
I would go on to learn there's some differences between electrical engineering and computer science. So electrical engineering, a lot of things in electrical engineering are analog. So, like in particular, the power grid, it's AC power, so it's analog, and it's a sine wave stuff that we need to worry about. And you know, they also have things like common filters. You know, they have like real-time things that they need to sort of monitor. But in computer science, everything is basically discrete in computer science. In particular, there's no calculus involved. So when there is calculus, maybe you model something as calculus, but you end up just breaking it into discrete parts. So while I didn't need to relearn really what a Jacobian was, there was some stuff that I did need to relearn. And that's what this is. So that's what I'm going to try to cover some of this, because I think that, I know I needed to review some of it when I started my PhD process, and I think that just from talking to people sort of in general, that folks weren't quite so familiar with that. So this is, I had given this talk before. Unfortunately, the one thing I have to cut out is the part about linear algebra. Vectors and linear algebra would be really important for computer graphics and for machine learning, but I don't know, hit me up afterwards when I can give you like a 2-minute thing on what eigenvectors are. If you want to talk to me on the breaks. Okay, so let's. So exponents and modules. So they're really good, especially logarithms, for analyzing algorithms. For this is really difficult because I can't see really what my slides say, and I can't really read my speed notes either. This is what happens when you have a great spoken public. Okay, this is what we're going to get to. So just review. Exponents. So hopefully this is already. This is how exponents work. You just put this little number over the top, and right. So an exponent just means you want to multiply the number that many times. So if you want to multiply x to the n times x to the n, you add the exponents together. And so if you set powers of 10, you say 10 squared plus 10 times 10 to the first, you add 2 and 1, and you get 3 things. and that works the same way, right? If you want to divide exponents, you subtract them. So m to the m over n to the n is m minus n, so 10 squared over 10 to the first is 10 to the 2 minus 1, 10 to the first. If they're both the same, you get 2 minus 2 is 0, so that's 1, and that's why the 0 power is always 1 no matter what you're raising the power to. And they can be negative as well. If they're negative, you use it as 1 over 10. So that's why 1 over 10 is 10 to the minus first power. Okay. They don't have to be whole numbers. They can be fractions, so x to the 1/2 is the square root of x to the 1/3 is the cube root of x, and so hopefully this is all you all remember this, right? So I think that while people remember this, they really don't remember what logarithms are quite as much. So logarithms are the inverse of exponentiation. So if x to the y equals z, then the log base x of z equals y. So just the opposite, raising the power, you're seeing what power we have to raise it to get that number. So if 10 squared equals 100, then the log base 10 of 100 equals 2, because that's the power, what power we have to raise 10 to get 100, that's 2. It works that way for the powers of 2 as well. And you know, you have 2 to the 64th is this big long number, 18 quintillion, blah, blah, blah. So I think there's 19 digits in there, right? So shorthands, generally, most people when they write things down, they just say log. That's often just the log base 10, if you're writing it down. The log base e is often, that's also called a natural log, and that's often abbreviated as LN. And sometimes people, because log base 2 comes up a lot in computer science, there's people use LG for the log base 2 or something. There's this useful identity that the log base, let's go back here. Maybe I do want the clicker because I can't do both of these. Where is the clicker?
It doesn't work.
What I was trying to say is that if you want to take the log base, you can only, if you want to take the log base x of something, it's the same as taking the log base k of something over the log base b of something. So you take any base that you want to just divide the one by the other, and you get that. What that really means is that I mean, I kind of want to see both, but it's whatever. I think I'm going to take this. So that means that if you want to find the log base 2 of something, and all you have is some way of taking log base 10, you take that value that you get from it and divide it by the log of 2 in the same base, and you get that log in log of 2. So, as an example, so what that really means is no matter what you base it at, you can kind of your other base by just dividing it by some scaling factor. And generally, if you're writing code, the log function is going to return the log base e, but often you don't care about it in log base e, you want it in log base 10 and log base 2, so you need to do some conversion. Now, you want to know why the logs are always base e in programming? Like, why the standard library is that rule in this?
Sounds natural.
Anyone take a guess? Liz?
Different default base.
Different what?
Like the base is still 8. Like the base.
No, it's almost always base e. It's always base
Because
e.
E is for exponent.
Because what?
E is for exponent.
E is
For exponent.
no. Well, the
Because
reason
whenever we do what do we call it? The way to make a program better, it could always end up being exponential.
no. So that's not it. The reason is that the way to calculate it is there's a power series, and the power series is based on the log base e because I think it just works out the way. If you want to calculate the log of anything, but it gives you the log base it uses. That's it. And anything else it gets in any other way just converts it. So it's like one, I forget what it is, but I'll check what it is. But, so that's fine. It turns out that the math in order to do any of the calculations internally is all based on. So you can do arithmetic in logs. So the log base anything of x times y is the log base that in to the of x and the log base something of y. If you wanted to have the log of a quotient, you subtract instead of add. So it should seem similar because you're doing the same things with exponents, right? And if you want to take the log of x to the y, that's y times the log of x. So for instance, if you want to figure out the log of 1, 2, 3, 4 times 5, 6, 7, 8, it's the log of 1, 2, 3, 4 times plus the log of 5, 6, 7, 8 from that, and then at the top, you get it's 3.891 and 3.791, but it's not exactly, they're really long things, and it's equals with 6.845. And so if we were to raise 10 to that power, we get this stuff right here. And actually, if we were to multiply them all out, we get, it's not quite the same, but it's within, like 0.1% of the real value. So why would you want to do this? Well, the reason you want to do this is because for a long time people didn't have computers to do this. They had to work this all out by hand using things like slide. Actually, I should say, anyone know what this is? Slide rule. And this is how people did any kind of complicated math before there were computers. They were tables of logarithms, and you would look up the number, you get the exponents, you get the logs of them, and you do the math for the logs in the logs because you can add them. So I just showed this up here because this is really well this. This is this circle that was actually nominated for a Hugo Award. It lost to Starship Troopers in 1960. So, what is this good for? So, one thing it's good for is like solving stupid computer problems, like in Project Boiler. There was this question of, well, actually it said, like, it basically said to prove or just show that those two big numbers, one of them is, show that the one on the left is bigger than the one on the right. So you could multiply that all out, but they're like millions of digits apiece. But you can convert them both sides to logs. So take the log of each side, and it should still be the one on the left is greater than the one on the right, And then you do this identity that I showed you on the previous slide. And you multiply those all out, you see what the log is of that number. And you multiply them all out like that. So that seems, right, so you can do this. The problem this is actually based on in Project Boiler, there were 1,000 of these. And you had to find which of them, it gave you the base and the exponent. And they were all like 5 or 6 digits of both the base and the exponent, so they were all going to be millions of digits long. They give you 1,000 of them, you have to say which of them is the largest. And if you did that, it would run forever probably. You have to do them all because they're all like big hints. But if you convert them to logs, my stupid Perl program did it in about a 10th of a second. So, and I wasn't doing anything fancy at all. I was just converting the logs and doing it. So you can still do math, even in the age of computers. You can do sometimes you can still do math a lot faster with logarithms than you can normally. Okay, so another thing. So suppose we have this. We have 8 words. We want to find new in this list. So because it's not sorted, the only thing you can really do is just start at the beginning and work your way down. You have to go through all of them, and finally, if you look for all of them, you get new at the end. So you have to start basically search for everything. And if you were to double the list, so suppose you had 16 words instead of 8, you would expect the runtime of this to double, right? Because it might have to go all the way to the end again. It might have to search through 16 things instead of 8 things. If you were to go to 32, you would expect it to be 4 times. Right? It's all pretty clear. You have to, in worst case, you have to look through everything. All right, so now suppose the list is sorted. So then we can be smarter. We can start in the middle at dog, and then say, oh, well, is GNU greater or less than? GNU is greater. So we only look through half the list. And we go to Fox next. and it was still greater than Fox. And we go to the middle again, and now we're at what? Maybe now we're at the middle, right? So now we found it. We found even 3 guesses instead of 8. And it's pretty clear that like no matter what the order is, we'll be able to find it in no more than 3 guesses because we keep dividing it in half each time. And it's also clear that if we were to double the number of things to 16, we probably only have to go 4 guesses instead of 3 guesses because we're still always dividing it by 4. So the number of guesses we're going to get is that x there. It's basically, well, in this case it's 8, but if it were 16, what power do we have to raise 2 to get 16? That's going to be 4. That's the logarithms, right? So probably you've been exposed to big code notation sometimes. Probably most of us have taken computer science classes, but let's run through this really quick and show how logarithms are. So this is always talking about like asymptotic time. So n is the number of things in your list or the number of things you need to process. And the question is, if you double n, what effect is it going to have on the runtime? So if you have an array, it doesn't matter at all because you can always go directly to that node. So if you have 1 thing or 1,000, then you can always get to it directly. And log n is that binary search that we showed you. You can always, whatever the power of 2 is of that. So log of 2, yeah, 16, the log base 16 is 4, so you can find it in no more than 4 guesses. Array scan is the first example I said. We're going to have to work through everything we have for just one time. Examples of n log n is sorting. We'll go into the details of how it all works, but for that, and then insertion sort is something that we do for twice, and then there's other big multiplication is n cubed. And then there's other things, often in brute force, it might take 2 to the n times or n factorial times. And those are really going to blow up and get really, really long times because the gravity just explodes and gets you big. So remember that number I gave you at the beginning, 64, 2 to the 64 is a number 18 quintillion, right? So you can't really brute force something with that. So, so my computer science professor would yell at me for doing this, but keep in mind that logarithms are not quite constant time, but they almost are, because you get huge numbers, they're still going to be just tiny little constants. So you can almost just throw away that logarithm. So binary search is basically constant time. And sorting is basically it's just going to be increased by the factor of, like how it's going to increase linearly by the size of your list. And so anytime you have an algorithm, you can divide things in half and then divide it in half and divide it in half, it's going to speed things up tremendously. So, so that's logarithms. We're going to move on to modulus now. So what is modulus good for? There's a few things. It's useful for all sorts of things. These are some of the things I'm going to refer to. So the modulus operator is what the remainder is going to be after you divide something. So for instance, so 5 by 2 is 1 because when you divide 5 by 2, you have a remainder of 1. 9 mod 3 is 0 because it's perfectly divisible over here. So right off the bat, that's one thing that's mod is useful. So I should probably preface to say that lots of times I know that people don't know what to do with a mod operator. You know it's in their language, but what do you do with it? Why would I want to check for? So it's one example. One right off the bat, you'll see is 9 divisible by 30. Very simple. So the syntax in lots of languages is the operator is the percent sign. C, Python, Perl are like that. MATLAB has a function called mod. In COBOL, you say something like divide x by y with remainder z or something like that. But pretty much any language is going to have something to do with that. What's it good for? So we always solve one. We already solve one. You can test whether something is divisible by something else. It also means that you can check whether a number is even or odd, right? So divide it, you take mod of 2, and if it returns 1, then it's odd. If it returns 0, it's even. That's really good. Time calculations. Given a number of seconds, you can see how many minutes there are by dividing it by 60 and then taking the integer part of it. And then if you mod it by 60, if you divide it by 60 and look at the remainder, that's the number of seconds that you have. Like if you want to do that any other way, it's like really, really complicated to do that any other way. But if you use a mod, it's like super simple. It's just one operator to do it. It's probably built into the, it's built in. It's an operator in the assembly language of your CPU as well. So it's like one instruction. Okay, another thing to sort. So this is like a little function that's just going a little snippet of code that's going to iterate from 0 to 20, and then it's going to print out that number and a number mod 5. And when we do that, what it returns? So it returns 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So this is a really simple way to do round robin. Because if you just keep integrating, like, otherwise think of what you want to do that. You have to put a statement in, if it's greater than this number that's equal to 0. And otherwise, you just use mod. You don't have to worry about any of that. Like, mod will take care of all that for you. And it's really well behaved too. If you have the two things to it, you want to add them together, it's always going to work out really well. This is another example, but it just basically does. FizzBuzz. I don't know why people ask this on programming exams, but we'll just review this anyway. Problem with FizzBuzz is you have to write a program that's going to print out the numbers from 1 to 100. If the number is divisible by 3, you say fizz. If the number is divisible by 5, you say buzz. And if it's divisible by 15, you say FizzBuzz. And I've heard tales of people writing huge amounts of code to try to figure this out. If you don't know about mod, it's really difficult to do this. Maybe you make a lookup table. Maybe you make, I don't know what you do. But, what? Regexes. You need regexes. And this is all you have to see. The only really tricky thing is you have to remember to do 15. You have to check 15 before you check 3 and 5. Because you want it because 15 is about 3 and 5. But that's it. Super simple. Once you realize you can use it for stuff like this, you start seeing applications for it everywhere. One more time. This is another Project Euler problem where you had to find the last 10 digits of this ridiculously huge number, which is a very, very large prime number. This is, I think, the largest non-Mersenne prime number that's known, at least when they wrote this problem. So I tried doing this 2 different ways. This first way took 2 minutes to run, which is not surprising because it's like kind of a million digits or something. I ran this, it took 0.155 seconds. And this is because Python, because this sort of operation comes up a lot in cryptography and checking for public key encryption and things like that. So there's a quick way to do it, which is build into Python. So it turns out that everything I could find says you have to use the PAL function to do it, but it's not true because if you just use the exponent operator, it does it as well. So you can look up modular exponentiation in Wikipedia, and it will show you how the operator works. I'm running out of time. Okay, let's go through trigonometry really, really fast. Okay, quick review of trigonometry. We've got a right triangle. We've got an angle theta. And so we've got this. I'm going to make it through it. So the sine is the ratio of the opposite side to theta. The cosine is the ratio of the adjacent side and to theta, and then the tangent is the ratio of the opposite to the adjacent sides. So I remember this by Somatella, which I learned in high school and it's used. Sine, opposite, adjacent, cosine, adjacent, hypotenuse, no, sine, opposite, hypotenuse, whatever, you can see what it says. So just like with logs, you always have to, they're always base E. If you're using sine and cosine functions in your favorite programming language, it's probably going to be in radians, not degrees. There are 2 pi radians at 360 degrees. And so this is how you can work between the two of them. We've all seen what sine waves look like. Sine goes between 0 and 2 pi, and it gets as high as 1 and as low as -1. And cosines look the same, except they start at 1 instead of starting at 0, so they're out of phase a little bit. This is another way of drawing it. This is a unit circle. So the radius is 1, which means that at any point along the circle, you can find the x-axis. The x point is the x-axis. The x point is the sine of theta, and the y coordinate is the cosine of theta. So this is the way to draw a circle. You can just take your the angle and you iterate it from 0 to 2 pi by some little amount, and you can it's the sine of your angle times radius and the cosine of the angle by the radius, and you draw a unit circle that way. So why is it always 2 pi and not pi? Well, no one really knows. I mean, people have said that because 2 pi comes up everywhere, why don't we just call tau 2 pi and do all the math this way? And it would be smart, and it would probably be better, except other stuff. This is my friend David Hand, and I think he sadly doesn't have a beard or mustache anymore. The last I saw him, maybe that's what he looks like now. Okay, so let's look at one little example here. So, just like I said that mod is really good for doing round robin, one thing that you can do with sines and cosines, I said that only the other engineers have to worry about sines and cosines and waves and things like that. Well, we can use them to our own advantages too. There's a program called trig downs, which I found on indentwithpython.com. It's not a long program, it's maybe like 100 lines, but this is really the meat of it. And I just want to focus on a couple of things. Is that that's really hard to read. I'm sorry about that. I should have made a different color. It sets step to be 0, and then every iteration is incrementing it like 0 to. And then at every point of it, it's saying that the y position should be the sine of the step. And it's like being scaled by 7. So because sine is going from -1 to 1, if you multiply it by the amplitude, it basically keeps moving it between -1 and 1 in this nice kind of skew. So it's kind of springy a little bit. It's a spring, I forget. Our spring sines and cosines are a little bit different. There's a spring bounce on a sine wave, but there's no friction. One other thing I want to say is you can't use the mod trick here. The mod only works with integers. So, but one thing you could do, because step is going to keep getting big and big forever, you could say that if step is greater than 2 pi, then you subtract 2 pi from step. But you don't really have to, because they're floating points, they can get super big. So, I think that I am just about out of time. So, more information, just like Wikipedia for all this stuff. That is the URL for, if you look for Invent with Python, there's all kinds of fun examples. I like that bouncing one because it's a good example of what you use science for. And there we go. I think I finished like right on time. So, anyone have any questions?
Just to be clear, big O notation is the number of steps in an algorithm, right?
Big O notation is, it's a function of, it's not quite that, it's more how is the runtime going to increase as the number of things you're processing increase. And there's always like some hidden constants in there which we don't pay attention to because they're going to, like, you're looking at asymptotic behaviors, so we don't really care, the constants aren't going to matter because the variables are going to equal the constants eventually. The reason you always use rating instead of degrees is the same reason. There's some power series that can calculate ratings. Anyone else? Have I like? yeah.
Can you figure out which quadrant you're in based on rating?
Yeah. Based on the rating, well,
Well, no, I mean, because I remember like coding something a long time ago where, like 18 or something, and like you could tell like based on whether it was negative or positive, it was in like quadrant 2 up here, or it was in 1, or
what is it,
the
Unit circle?
for the triangle.
oh,
Sorry.
well, I mean, you look at the angle, right? The angle is only going to be in 4 different, things, 4 different things. So let's go, if we go back to here. I mean, the angle, there's only 4 different ranges, so you can just set ranges, really, that's probably about it. Yeah, that's probably the simplest thing. I mean, otherwise, you could look at like X, you could look at the side of this. Yeah, and other examples of using sines and cosines for, you know, in linear algebra. So maybe next time we'll do like linear algebra for remedial linear algebra will be my next
In common cultures.
and common, but that'll be the year after.
Okay.
Anyone else? Does anyone, has this been like new to everyone? Is there, do people know about like what's used mod for, and people like, yeah. No, a few people are sort of shaking their head, people are, I don't know what people know about that. Was this like new for folks?
I feel like half of it.
Half of it new, that's kind of what I was aiming for. Like, I kind of remember this, but I kind of don't remember what to use it for.
So when you were revisiting these topics in your PhD, was there anything really significant with like changing your perspective of how you could apply this? Or was it all
Mostly for linear algebra. Yeah, I was a math major in college, and I don't know that I ever really learned linear algebra really well. Until I took a computer graphics class, because everything in computer graphics is linear algebra. And then everything in machine learning is really linear algebra too. Like, once I learned what an eigenvector was, it all made more sense. It took a while. I actually found a website that explained it in about like 2 or 3, like very, very simple. It's like, oh, that's all that means. So yeah, do you think you spent all this time like row reducing matrices and things like that, which I think are kind of wasted lines. But you have to think a matrix is a function that takes one vector and returns another vector. If you think about it that way, then everything else makes a lot more sense. Otherwise, yeah, because then you can think about matrices that are changing the space that the vectors are in. It's a lot more interesting there. So, yeah.
Can you tell us the name of the website for explaining?
I think I had trouble finding it.
Khan Academy has a good explanation. That's about 10 minutes.
If I could find it, I will. I guess I will put. I don't know how they have a procedure for sending out slides. But I don't know. I'll find some way to get it out. Or I'll put it up. Maybe I'll put it up. I think I don't even have my website here, but I don't know. Come next year when I. There are some good pages to talk about this without or just we'll chat it. Might take me off the case. All right, so they're kicking me out. They're not kicking me out, right? I thought it was done now. Wait.
You got 5 minutes. I think it says
It's
5
not 5 minutes? Oh, I thought it was already 10 12. I thought I had 20. I thought I had 30 minutes. That's why I was like.
You got till 11.
Oh, I have till 11.
Yep.
Oh. You want to see? Let's do what I Alright, so right. This is the important thing. The matrices are functions that take one vector and return another. So so then like these transformation matrices that you use a lot in computer graphics. So what do I have? I don't even read these slides, but So the first thing, you stretch by k's. What those are doing is saying it's only going to increase the x value by k, but it's going to keep the y value the same. What you do often in computer graphics is your image is a bunch of pixels. So instead of this just being x and y, it's going to be a whole bunch of x's and y's, which are the things in your pixel and in your image. And if you multiply all of them by that k001, it's going to just change everything for the x values and not everything for the y values. And similarly, you can rotate it around by using that. You can skew things too. So this is crazy. I think I pulled this right off of Wikipedia, showing how, again, it's taking all the pixels from that, and you're just multiplying all the pixels by those matrices, and it's spreading. It's only moving it in the x direction and not the y direction. So. Okay, right, so let's put all of this up here. Okay, let's say that I have this matrix, 2, 1, 1, 2. And then I'm going to multiply it by a whole bunch of vectors and see what we get back. So if I say, if I take that by, if I multiply it by the vector 1, 1, I get 3. If I multiply by 1, 2, I get 4, 5, and so on and so on. I'm going to put this all right? All I've done is multiply out a bunch of vectors. So the ones in red, which are probably impossible to read now, they are the same value as they're the same value as what got put in, so they're not changing at all. So if I say a times 1 minus 1, they get 1 minus 1 back. Right? And same for 2 minus 2 and minus 2, 2. Right? The ones in blue also, you just get multiples of what you put in back. Right? So the vectors, the vectors where you get the same, when you multiply that matrix and you get a multiple of the vector back are the eigenvectors of that matrix, and the amounts that they get scaled by are the eigenvalues of the matrix. And that's what I'm showing here. I know so. Here, I looked at these in 3.5 years. Right, so a matrix maps one n-dimensional space to another one, and some vectors change the length but not the direction of it. So for some of them, right, these are some of the slides that I skipped. But sometimes it changes the length and the direction of it, and sometimes it only changes the length. And so the vectors that do that are the eigenvectors, the amount that gets scaled by the eigenvalues of it. So those are really important. Those are like the characteristics of this. A good way of describing what that matrix is doing and the effect that it has on space. Lots of times in machine learning, you end up in any side of data science, you get tons of these vectors. It might not be just dimension 2, there might be dimension 50 or something like that. But only a few of them are going to get scaled by big amounts, and the other ones are going to be little amounts. And the ones that scale it by large amounts are going to be more important to understanding what's going on with the smaller values. Those are called the principal components. Now I think I'm out of time, but does it make more sense now? That was my like 5-minute super compressed overview of what eigenvectors are.
Good job.